Okay. So dehydration, it's either E1 or E2, your elimination reactions, which hopefully you guys remember. But let's start with the one that you know for sure. Whenever we have an alcohol group reacting with H2CO4, SO4. So we know that we always need some sort of acid because we're doing an acid catalyzed dehydration design. We're doing the opposite of what we learned in addition reactions. And now, do you guys remember when to follow the E2 or E1 mechanism? No? Okay, so remember, if it's E2, it has to be everything in one single step. So if the alcohol, its primary, is gonna choose to go with the E2 mechanism faster. But if you have an alcohol that's secondary or tertiary, you're gonna be following your E1 mechanism. So in this case, if we start by looking at our alcohol here, what's the degree? Primary, secondary, tertiary? Secondary. So what mechanism am I following? E1, exactly. So in the very first step, we know that we need to make our alcohol group a better leaving group. That's gonna be with the help of the acid. We just make it better. Now it can finally go and you form your intermediate, which is a little carbocation in here. Okay. So what's gonna happen next? Do you guys remember? Rearrangements. Remember, whenever you see a carbocation, you're gonna do rearrangements. So in this case, that carbocation, primary, secondary, or tertiary? What is it? Secondary. How can I make it better? Methyl shift, exactly. Yeah, I just moved my methyl group over here. So I end up with my tertiary carbocation. Okay. So far, do we all see that? Is that clear? Okay. Now, remember that for elimination reactions, it was all about your beta hydrogens. So wherever the carbocation is, that's always your alpha position. Okay. Meaning that the carbons adjacent to that are the beta carbons. So we're only going to be attacking those carbons connected to those carbons. So overall, how many different products am I going to form? 2, because remember, the methyl groups, they're equivalent to each other, okay? Because the single bond is going to be constantly rotating, so they're going to yield the same exact product. But let's just draw out our product. And then here, there was a typo. That was supposed to be the product. Plus, also you have your minor product, which is going to look like this. Like this. Okay, but remember, your goal is always going to be to create a molecule that's really, really stable. Okay, that way it's not going to be reactive. Everyone's going to be happy. As far as double bond stability, the more substituents you have, the better it is. So in this case, we just followed our E1 mechanism. Yes.
How did you get the beta to the final result?
So for that, I was attacking, let me erase this so it's clear. I was attacking my beta hydrogen with the help of my conjugate base that came from the acid. In this case, I'm just going to represent with an A minus. So your base ends up attacking your hydrogen, and then the electrons move between alpha and beta carbons.
And that acid base is from H2SO4, right?
Mm-hmm. Okay, this should just be a review from Orgo 1. So far, questions on that? Do we remember that? Little, okay. Now, we are still on dehydrations, but this time we're going to be using a new acid, which is going to be POCl3. Okay, this guy is very important, okay, because you might get a conceptual question on this. Now, I don't know the exact reason why it happens, but whenever POCl3 is used as your acid, you're always going to follow an E2 mechanism, no matter the degree of the alcohol group. Again, this might be a conceptual question, so keep that in mind. So far, questions on that?
Can you just repeat what you said again? Sorry. The last thing you said.
POCl3, it might just be a conceptual question. It's always gonna be E2. Okay. So far, questions on dehydrations. It's just elimination reaction. Okay, now. Another kind of conceptual question is gonna be, which one is gonna dehydrate the fastest? So, which one do we think it is? What am I looking for? What kind of alcohol group? Why a tertiary one? What did we say? It's gonna be more reactive. It's gonna give you the most stable carbocation, the most stable intermediate. That's why it's gonna be a lot faster. So whenever you're trying to find the one with the fastest rate, you're looking for the most stable. So technically, it's gonna be first benzylic, then allylic, and then the normal trend that you guys know, tertiary, secondary, and primary. So what's gonna be the answer for that one? You think it's gonna be A? It's gonna be that one exactly. Because this one has a tertiary alcohol that's also in the benzylic position. Okay. So far, questions on that?
From this one, the benzylic is the most stable.
Yes,
It's going most stable to the least stable.
exactly. Because remember, benzylic and allylic, they are so special because of the resonance that they can make. Resonance stabilizes the charge, which is gonna make it overall better. Okay, do we have any questions on dehydrations? Does it make sense? Oh, yes. For the you don't have to worry about the mechanism. You're never gonna get a question on the mechanism. Literally, the only question that I've ever seen him ask is, if you use POCl3 in a dehydration of an alcohol, what of the following mechanisms follows? SN1, SN2, E1, or E2? You don't have to worry about it. Yeah, you're good. But technically, if it's an E2 mechanism, remember, wherever the carbon is connected to the alcohol group, this is going to be your alpha position, and adjacent to it are the beta ones, right? Now, for elimination reactions, we need beta hydrogens. Do both beta carbons have beta hydrogens? No, the one on the right doesn't have any hydrogens. So the only product that we can make is with the left one. So that's why we only get one product, and where the double one is to the left side. Okay, any other questions? We're good? Make sense?
So the beta only appears where there's a hydrogen on the side.
The whole purpose with elimination reactions is that you need beta hydrogens, no matter the mechanism. E1 or E2, but you need beta hydrogens. Otherwise, the reaction cannot proceed. Okay, we're good? Okay, now let's start talking about carbonyls, which is going to be the main focus of the next two chapters. Okay, before we even get on with the reactions, we have to know the reactivity of carbonyls. That's going to be very important. Now, as far as reactivity goes, everything is going to be based on steric hindrance. Okay, that's going to be your main factor, steric hindrance. Okay, now, hopefully you guys remember the names of those functional groups. So the very first one, what's the name of the functional group? Carboxylic acid. Whoops, carboxylic acid. Next one, aldehyde. Third one is your ester. And last one, ketone. Okay, now, if we know that the reactivity is based on steric hindrance, which one do you think is going to be the most reactive? Most reactive. It's actually going to be the aldehyde, because what's bigger, a hydrogen or a carbon? A carbon is going to be bigger, so it makes it slightly bulkier. So if you have two carbons, they're slightly bulky, but if you have carbon and hydrogen, hydrogen's way smaller, so I have more space to attack. Okay, question. Steric hindrance is basically whenever you are connected to a bunch of groups. So whenever there's a cluster. So for example, if you have, let's say, a molecule that looks like this versus a molecule that looks like this, we have a lot more branching on the left side, making it more steric hindrance. The one on the right doesn't have that much steric hindrance.
So like all here.
Bulkier, yeah. Okay. So now let's just start doing our ranking. So we know that the aldehyde is going to be the most reactive. Then what's going to follow? It's going to be your ketone. And then it's just going to be your carboxylic acid. And last one is going to be your ester.
So the most reactive is going from the less bulky to the most bulky.
Mm-hmm. Because at the end, once we start talking about the reactions, it's going to be all about the actual carbonyl. Why? Because remember, whenever you have a carbonyl, a carbon double bonded to an oxygen, there's a dipole moment, right? The oxygen is pulling away all of the electron density towards itself, making it delta negative and leaving the carbon as a delta positive. That delta positive, based on the steric hindrance of the carbonyl, that's going to be your attack side, okay? But we're going to talk more about that once we go through the reductions. But so far, questions on that? Does that make sense? Yes. So it's all based on steric hindrance. Why? Because the smaller the carbonyl, the easier it is to attack the carbon in there, okay? It's all based on that. Questions on that? We're good? Make sense? Okay. Now, let's make it slightly more complicated. This time you only have aldehydes and ketones, but I want you to rank them from most to least reactive. You guys have 2 minutes. Yeah.
The least would be this one. No. I mean, this number 3 would be. Yeah, it would be the least, because it's the more.
Yeah.
Bulky. So this is definitely the most every. No, this is the 6. Yes.
Okay, do we need a reminder of the time? We're good? Okay, which molecule is the most reactive? We have 2 different aldehydes, but specifically, it's gonna be number 4, because this one has connections to pure hydrogen, so very, very small. There's not that much steric hindrance, it's easier to attack, therefore more reactive. What's gonna be the second one? Number 2. That's the only other aldehyde. And then we're just left with ketones. What's going to be the third most reactive? Beautiful. Fourth,
Six,
fifth,
one.
and very last one is just going to be 3. Because we're just starting to branch off more, so it's going to be harder to attack the carbonyl. So questions on that? Again, it's all based on steric hindrance. Okay, makes sense. Okay, let's get started with the reactions themselves. So this chapter is gonna be about redox reactions, which they are something you guys probably learned back in general chemistry too, maybe? Yeah, one of those. But either way, let's just quickly review our definitions of oxidation and reduction. Now, I know that in general chemistry, we were focused more on the electrons and all of that, but now that we're in orgo, we can simplify it even more. So whenever we are talking about an oxidation, that means that you are increasing the amount of bonds between carbon and oxygen. But when you're doing a reduction, that's the complete opposite. You're reducing the amount of bonds between carbon and oxygen. So if we look at the little diagram in there between those 3 molecules, I'm starting with an alcohol group, I'm going to an aldehyde, and then a carboxylic acid. So the forward direction, is that oxidation or reduction? It's oxidation, exactly. Because on the first molecule, I just have 1 connection between carbon and oxygen. On the next one, I have 1 and 2. Then very last one, I have 1, 2, and 3. And then that means that the reverse reaction is just your reduction. Simple as that. So oxidations, they make your carbonyl. Reductions, they make an alcohol group. Okay? So far, does that make sense? It's very simplified. Okay? Now, let's start with reduction, which is what your professor was covering today. So hopefully he mentioned those 2 reagents. When you see the little SpongeBob. Now, what's the main difference that you see between the SpongeBobs? One of them is way stronger than the other one. Exactly. So that means that your sodium reagent is going to be your weak reducing agent, but your lithium reagent, that guy is very, very strong. Okay. Now, again, if it's a reduction, I'm going from carbonyl to alcohol group. Now, we just talked about reactivity of carbonyl groups. So we know that aldehydes and ketones, they're very small, so they're easy to attack, right? Okay, since they're easy to attack, whenever I want to reduce them, I don't need something that's really, really strong. I can work with something that's weak or strong. Both of them are going to make the same exact work, okay? They're going to make the job. But if we have something that's less reactive, like a carboxylic acid or an ester, those guys are not as reactive. So we need a little bit more strength. So that's going to be whenever your lithium reagent comes into play. So let's just summarize that. Your sodium reagent can only work with ketones and aldehydes. Okay, why? Because they're very reactive. So they're easily reactable with either the sodium or the lithium reagent. But the other one, this guy is going to react with all of your carbonyls because it's so strong that it can take anything. Okay. Now, conceptual question. Okay. You don't only have to remember the actual reagents. You need to know the specific nucleophilic species. I'm not sure if he mentioned that in lecture, but best guess. What is it? Is it just a hydrogen? Hydride ion, exactly. So this guy, actual species, is going to be a hydrogen with a lumper and a negative charge, which is your hydride ion. Okay. So far, questions. We just talked about the concepts, basically. Nancy. Reductions is from a carbonyl to an alcohol group. Okay, now. The next portion is basically a summary of the reactions, but before we even do that, let's look at the actual reactions and their mechanisms. Okay. let's start with this one. So again, as we were mentioning, with the reactivity of our carbonyls, we know that there's a little dipole moment here, right? Meaning the oxygen is delta negative, carbon delta positive. Okay. If we know that the reducing agent is the one that provides the nucleophile, which we know is going to be whatever hydrogen is presented in that reagent. In this case, it's just going to be a normal hydrogen. But keep in mind that you can be given isotopes. Nancy. No, we did not. Not yet. We're waiting for it. Yes. Okay. If I know that this is my nucleophile, that means that my carbonyl is going to be my electrophile. Hopefully you remember that electrophiles tend to have a positive charge. In this case, my only partial positive is going to be specifically the carbon in here. Okay? So far, we good? Make sense? Okay. Now, nucleophile, electrophile. Of course, we're going to have a nucleophilic attack, meaning that your hydride ion goes and attacks in there. Now, keep in mind, if it's a nucleophilic attack, whatever did the attack is going to get connected in there. So if we make a new connection to that carbon, I'm going to have 5 bonds. So how would I fix that? You're going to move up your electrons towards the oxygen, so you don't break the poor octet in there. So far, I have the legs of my little aldehyde. Now I have an oxygen minus. And now, look, I just connected whatever hydrogen was given in the reducing agent. Okay? So again, first step, just nucleophilic attack. That's it. Simple as that. Now, how am I going to finalize this reaction? What's going to happen? Do I do it again? Do I attack again this carbon again? We need to create our alcohol group in this case. So the only thing that I'm missing is just a hydrogen. So for that, whatever solvent you were given is gonna do an acid-base reaction, meaning that your oxygen is just gonna take one of those hydrogens. So we end up with this little guy. Okay, now I just created an alcohol group specifically. What's the degree of the alcohol? Primary or tertiary? Primary, remember, only connections to carbon are going to count as R groups. Okay. Primary alcohol. So now we can start going back to the little chart in here. So we know that for aldehydes, whenever we reduce them, we always end up creating a primary alcohol. Okay. So far, questions on that? The mechanism is very simple right now. Okay, make sense? Yes.
The nucleophile, is it from the NADH4?
Yes. Okay, now. Same reagent, but we're starting with a different carbonyl. What's the name of that guy? Ketone, beautiful. Now, same process. There's a dipole moment. Carbon has delta positive, oxygen delta negative. Again, I'm just gonna take my hydride ion from the reducing agent. I do the nucleophilic attack. I get connected in there, and then you have to kick up your electrons so you don't break the octet. So right now I'm creating my oxygen minus, and I just connected my hydrogen in there. Now, same as before, with the solvent, I'm gonna do my acid-base reaction. So I end up with this guy in here. This time it's a secondary alcohol. Exactly. So now we go back to our little chart. This guy is always making secondary alcohols. So far, that makes sense. Pretty easy to follow. We're good? Question? The difference is just the starting molecule because we're using the same reagent. Okay, good. Okay. We're good? Now, in this case, I reacted with my aldehyde and ketone and I used the weak reducing agent, but could I use the strong one? Yeah, I can use a strong one. So for, again, aldehydes and ketones, they're so reactive that they're gonna react with anything, weak or strong. But now, if we're trying to do the same reaction, a reduction, but we're starting with an ester or a carboxylic acid, what kind of reagent am I gonna use? The lithium reagent, exactly. I need something that's really, really strong. Now, same process as before. Let's just start by looking at our dipole moment. So our dipole moment gives us a partial positive in the carbon, partial negative in your oxygen. This time I'm given the lithium reagent, but still same process. My nucleophilic species is whatever hydrogen is presented there. So there's my hydride ion. Okay. I do my nucleophilic attack. I get connected in there, so you kick up your electrons towards the oxygen. I have an oxygen minus now. And there's my hydrogen from the nucleophile. Okay, what's next? In this case, we just protonated. Let's go back to the mechanism in here. So when we were reacting with our ketones and aldehydes, basically look at the legs of your carbonyl, okay? Aldehyde just has carbon and hydrogen, okay? Ketone just has 2 carbons. So those connections between carbon and carbon and carbon and hydrogen, they're very strong. But whenever you're given usually a heteroatom, like oxygen in this case, that one we can break it because it's actually gonna act as a leaving group. So we have to be a little more careful. This leaving group is gonna prevent my acid-base reaction at this step. So what ends up happening is that, I don't like the leaving group. It's a little too unstable. So I'm gonna kick it out by reforming my double bond. So electrons in my oxygen go back down to reform the carbonyl, and then I kick out my leaving group. Which means that now I have a carbonyl with 1 methyl group on that side and a hydrogen on the other side. And now we have to keep track of a byproduct, which is the leaving group. We have an oxygen minus with 1 carbon chain. And again, that was your leaving group. Okay. So far, does that make sense? Okay, we're good. Now, we have an aldehyde. Yes.
That's a double bond, right? On the newly formed aldehyde.
Yes. That is a double one. Yeah, let me actually just do it in black so it's easier to see. Okay. Now I have an aldehyde. Is that my final product? What do I do?
Turn it to like the aldehyde reaction again.
Exactly. Remember, the whole purpose with reductions is to get rid of my pi bonds, basically. So if you see any carbonyls, I don't want that. I'm going to keep going until I get rid of every single carbonyl that I see. So at this point, they should be somewhat familiar. It's the reaction that we just did. So again, same process. Your hydride ion does the nucleophilic attack, and you kick up your electrons. So now we end up with oxygen minus the hydride ion from the first nucleophilic attack. And now I have a second hydride ion here. And I still have my byproduct. Again, that came from my leaving group. So far, does that make sense? We're good. Okay, we're keeping track of everything. So now, what do I have to do? Now we can protonate with whatever solvent we were given, which in this case it was H3O plus. Okay, let me just redraw H3O plus in here. So again, both oxygens are just gonna go and grab one of those hydrogens. So we end up with this guy. Okay. In this case, those two guys are my products. What kind of alcohol did I just create? Primary. Exactly. So now we go back to the little summary. So we know now that when esters are reduced, you always create a primary alcohol. Okay. Does it make sense? Pretty easy to follow, right? Okay. Now, let's complicate it a little bit more. This time, we're still going to start with an ester, but we have a cyclic ester. So for this one, I'm going to give you guys 3 minutes to try and figure out the full mechanism along with the product. You guys can take a look at your notes from lecture, talk with each other, but give me the exact full mechanism, and then I'm going to ask for a volunteer. Again, 3 minutes, guys. Okay, and you have the previous mechanism as a reference. Now, a little hint. Remember that we have a leaving group, so that has to go away. In the example that we just did, we had a linear structure, but if you start with something that's cyclic, everything is going to be hanging out from the same molecule, meaning that there's only one product. So keep that in mind. Keep track of your carbons. Do you have a question? Question?
We did. Like, how many?
Don't worry. Okay.
This is gonna make a leaving group,
Mhm.
but how many would it take with it? Is it only the oxygen from the leaving group?
So
would
for
it be-
the previous leaving group, we basically just cut the connection between carbon and oxygen.
Right,
That's the only thing
right.
that we're cutting open.
Yeah,
So if we go back to that cyclic structure,
so it's
Um,
just the carbon and the
exactly,
oxygen?
I'm just cutting right here. So everything is gonna be hanging out
Oh,
from this
okay.
carbon. So everything is in one linear chain.
Oh, okay.
That's
but
why I told
it's
you-
not really a leaving thing. It's still gonna be.
You
connected
kick it
there.
out. Yeah, it's still gonna be connected, but
Well, how many would you got? Just the oxygen? Or the oxygen connected to that?
the oxygen is still gonna be hanging out from this carbon. The only thing I'm erasing is this connection.
Oh, okay.
Everything else stays the same.
So it's not a leaving group because it's on the end of the chain. It's not leaving, it's still connected to it.
Yes, but the correct term is still a leaving group.
Okay.
But yeah, but still, you got it. Yes.
Would it open? Or
Great
no?
job. You got it.
Okay. Like, just open by
You got it.
itself? No. Or is it, because I remember there's something that's involved.
Okay, did we get a product? Do we still need one more minute?
Open it.
You guys need to speak up, otherwise volunteers. One more minute? Okay, one more minute.
So it's, all the heights, so the ages. So it's the same thing? Yeah. Yeah, and then you just attack it with the. With this one. So this doesn't really attack. Yeah. This one. This. So this one, is the eyedrop. Yeah. Here. So your eyedrop is this from here. No, yeah, I don't use this, yeah. So this, I can just like erase. Just look like that.
So. Yeah, open it.
So, oh, okay, negative.
So the other one is-
Okay, can I get a volunteer to show me the mechanism for this one? Volunteers or victims, guys? What are we choosing?
This already.
Did we get a product so far?
Yeah.
We didn't get a product? We're just waiting? That's not good.
Exclusively on
Okay. Do you get it? Go. Right.
I mean, like this.
Okay, let's see.
Because the makeup.
So if you're asking a question, we can't hear you. So just type whatever question you have. Beautiful, your hydrogen ion. Does the nucleophilic attack kick up the electrons to the oxygen? And we still have a cyclic ester. Well, not an ester, but okay. We have the hydrogen from the nucleophile and then the oxygen minus from the carbonyl. Beautiful.
This one was strong.
Now, exactly. We have to reform the double bond so we can kick out our leaving group, which basically we're just erasing that bond between carbon and oxygen. So now everything is going to be linear. You have, there you go, an aldehyde. And then we keep track of our carbon chain. Right. 4N, beautiful. Now what happens? Another hydrogen comes and does the nucleophilic attack, kicking up the electrons. So now we don't have any more double bonds. Everything is just pure single bonds. That's my hydrogen from the second attack. That one's from the first one. Oxygen minus, and also on the byproduct. And now we just have to neutralize everything with H3O plus, the solvent that we were given. Yes, you can just select it if you want. Yeah. There we go. We're simplifying our work. And then we end up with beautiful alcohol groups in there. And what are the degrees of those? They're both primary, exactly. There you go. And great job. You got it. Yes, please applaud her. Yeah, she did an excellent job. Okay. Did anyone get the same product? No one? I just see one yes. Right now, we just got it, we're following. Okay. Now, questions on the mechanism. While she was drawing, I was just walking you through the mechanism. We're good? Wait, okay. Now, next reaction we're gonna do is gonna be the same one. We're still using the lithium reagent, but this time we're starting with a carboxylic acid. But same exact process, guys. That alcohol group from the carboxylic acid is my leaving group, okay? So it's the same exact mechanism. Volunteer to do that from scratch. Same exact mechanism, just different leaving groups. Volunteer or victim? Okay. Over here, I saw a hand that was raised for the previous one, so why don't you give it a try?
Yeah, you can expect us to overlap.
alcohol, we already have alcohol.
Give it your best try. Well, yeah, you're right, but
It's gonna
still.
open them up, but it's-
It would be like.
just give it your best try. You can use the previous ones as a reference.
No, yeah, I know. No, I'm just-
There we go. My hydride ion is there.
This hydrogen
Nucleophilic
attacks
attack, beautiful.
it's
And then we
like
got
this,
electrons.
this, right?
We have our alcohol group in there.
No, like this hydrogen.
O minus, and now we have a connection to a hydrogen. Beautiful. Now, what do we do?
So from the lithium. Okay, and then attach this. And then it. Yeah. And then.
What do we do now? Look at the previous one. If we know that we have a leaving group, now we can reform our double bond. There you go, and kick out your leaving group. So you end up with one aldehyde, and now your byproduct is just an OH minus, just floating around.
Oh my.
Great job. Okay, no, I still have a carbonyl. We don't like that, so how do we fix it?
Or you just know.
There we go, another hydride ion comes around, attacks it.
The reaction.
So now we end up with pure single bonds. Oxygen minus. There we go. And then we're just gonna make everyone happy with an acid-base reaction.
Yeah, I need to.
H3O plus, exactly.
So just remember, lithium boride doesn't react with.
And we end up with our primary alcohol, plus water, in this case, is your little byproduct. Yeah, because that OH minus now gets one hydrogen, so H2O, H2O, sorry. There we go, and great job. You got it, you did it from scratch.
Hey, thank
So now we can applaud him too, because he did this from scratch. Okay. Okay, now, it was the same exact mechanism. The only thing that we changed was the leaving group. That's it. But again, same process. Nucleophilic attack, reform your double bond. Again, another nucleophilic attack, and we end up with acid-base reactions. That's it. Now everyone's happy, everyone's neutral. We don't have any more double bonds, so we're happier. And yes, let me. It's gonna be this guy, which is just your primary alcohol plus H2O as your water. And then let's keep track of our hydride ions. So this one, it's right here, in your aldehyde from the first attack. And then this is my second one. And there we go. And then our little byproduct is here. Okay. Questions on the mechanism? Does it make sense? Easy to follow? Okay, great job. So now that we know how to do reductions for aldehydes, ketones, esters, and carboxylic acids, now we can make a little summary of that. Because again, remember, you're not gonna get questions on the exact mechanism. So as long as you remember the transformation, You are good with that. So let's just start writing this down in here. So let's start with a ketone and an aldehyde.
Yeah. I think just like going over it.
Okay. So that right there is just a little summary of what we saw in the reactions with ketones and aldehydes. Okay. Now let's do the same exact process, but for your esters and carboxylic acids. So let's just draw.
Yeah, I'm guessing that for the exam, we don't. But knowing me, I will need to know. Just like. what
The
you
re-
draw.
the reaction.
Just
Oops,
explain
that's
what-
wrong.
Oh, yeah, I need to understand.
Okay, so what we see right there, it's summarizing everything. Again, some students prefer to know the full mechanism. Some students just like to see the shortcut. Question? Yes. Okay, there we go. So again, if you feel like shortcuts are gonna confuse you, please do the mechanism. Stick to whatever feels more comfortable for you. Yes, primary. So yeah. So if, do we have any last minute questions? Did everything make sense so far? Okay, and quick recap. What was the most reactive carbonyl from what we just saw? Most reactive? Aldehyde. What was the least reactive? Ester. Yes, so great job. Now you guys are free to go, and I'll see you guys Wednesday. Don't worry, that's still gonna stay up. But if you have any questions, just come up to the podium. That's why you go from a carbonyl to an alcohol. A carbonyl has 2 bonds between carbon and oxygen. Alcohol, 1.
Wait, but like just simply memorizing the product and that we need to know the steps.
Okay.
How you have to ask.
That's a carbonyl. I have 1 and 2 bonds. But if now I turn this guy into an alcohol group, now I have only 1 connection. There you go.
I'm part of the other.
Oh, Dr. Roche,
But I don't have access to this.
do the handout.
Then I
Uh,
need to know.
I joined the
Yeah.
percentage, but
I'll post them there then. So yeah, no problem.
I have a question. So for the exam, should we just remember can we just remember like the reactant, the product, or should we know the steps too?
Not really.
So we
You don't have
memorize,
to know the full mechanism. I just like to explain it because some students find it more helpful than just memorizing
okay.
just this. So
Alright.
yeah.
If they're gonna be like different, I'm still gonna need to learn. Thank you.
Thank you.